Booster Alpha's go for flight.
Fine. I'll do it myself.
Starship is a fully reusable, super heavy lift launch vehicle under development by SpaceX. Starship will carry both crew and cargo to Earth's orbit, the Moon, Mars, and beyond. Starship Mini will be an affordable, functional model rocket that can take off and land autonomously. Let's break down the key components of the development process for our Starship Mini. This is Jenkins Robotics.
Alright you guys, let's go ahead and talk about the Starship Mini. The goal of the Starship Mini is to make a vertical takeoff and landing model rocket capable of reliably performing a similar flight profile as the Starship. As you can see in this animation, there's 3 stages of the Starship flight profile. The first stage is powered ascent. This is when the rocket will be accelerating vertically and using the engines to keep a nice controlled profile. After the rockets burn out, we'll be entering our second stage, coasting. During the coasting, we'll be reaching our highest altitude. The rocket will maneuver itself to a skydiving position, doing a belly flop. This will increase the drag and slow the rocket's descent. Using the flaps, it will be able to control itself same way as we were using the engines during the powered ascent stage. The last stage will be the powered descent. This will begin a certain distance above the ground, and the rocket will reignite its engines to slow itself down. Ideally, you will hit the floor with a net velocity of 0. So, how will the Starship Mini actually perform this flight profile? Well, the Starship Mini will have some key components. The first key component will be the aerodynamic control surfaces. The Starship Mini descends under active aerodynamic control. This is accomplished by independently moving the 2 forward or the 2 rear flaps of the vehicle, which is powered by the control surfaces servers that will be housed in the top of the rocket. The second set of components that we'll be having on our rocket will be the avionics. The avionics and the flight computer will provide real-time control of the rocket. Starship Mini is fully autonomous, and it will be responsible for maintaining the intended flight profile and performing precise landing at the intended location. The flight computer will do this by taking the data from onboard sensors and controlling the TVC gimbal and the aerodynamic control surfaces to keep the rocket flying nominally. The last set of components on this rocket will be the thrust vector control. Starship Mini will contain 4 rocket motors, each on a 2-axis gimbal that will provide thrust vector control for a total of 8 TVC servers that will be housed on the bottom of the rocket. So let's talk about how exactly would thrust vector control work. Thrust vector control is the ability of a rocket to manipulate the direction of thrust from an engine to control the altitude and the angular velocity of the vehicle. So, looking at the diagrams I have in front, a single rocket engine can tilt its engine left and right, up and down. This will allow the rocket to rotate about its center of mass. This can be used to adjust the rocket's tilt and yaw. However, this cannot control the rocket's roll. Because the single motor is in the center axis, you have no roll control. The Starship Mini, however, uses two motors during the powered ascent and descent stages. We can still have pitch and yaw control, but we will also gain roll control. By manipulating the engine to different directions, we can control the roll of the rocket. Not only can we control the roll of the rocket, we can even have dynamic thrust control. One of the key difficulties with landing with model rockets is the inability to throttle a rocket's engine. However, Starship Mini, using the two separate motors, will have dynamic thrust control. As you can see, by vectoring the engines in two different directions, we can control the vertical and horizontal output forces of the rocket. So, if we want to decelerate quicker, we can point the two engines vertically up and down to provide more force in the Z direction. However, if we feel that the engines are producing too much thrust, we can vector our two gimbal engine to waste some of the excess force to the sides. This will allow us to decelerate slower, giving us a form of dynamic thrust control. Starship Mini will be an advanced model rocket and will require a robust development process. Just like SpaceX, we'll be conducting a series of rapid prototyping and testing, beginning with the development of Starhopper Mini. Starhopper Mini is a smaller version of Starship Mini. As you can see, Starship Mini will contain 4 rocket motors, 2 being used for ascent, 2 being used for descent. Starhopper Mini will only contain 2 pneumatic motors, powered by compressed air. Using the Starhopper, we'll be able to conduct long duration test flights. This will allow us to easily and cost effectively test and optimize our flight software and key mechanical components. We will be able to develop our ground control station that will monitor and control the rockets wirelessly, and we can develop our launching and landing platform. We can do all of these in a time effective and cost effective way. Ideally, Starhopper Mini will allow us to develop a very robust control system before we ever make our first Starship Mini. Once we determine our rocket and our software is ready, we can then move on to the Starship Mini.
If you want to be a part of the community and have influence over our project, join our Discord. The links are down below. Special thanks to Trev Finley for becoming our first patron. If you too want to support us, consider becoming a patron. Patreon supporters will also get access to our VIP Discord channels. The links are down below. Thank you, and see you next time.